Okay, good afternoon. Thank you for joining us on this session. Please remember to use the chat as well if you've got any questions or any comments. And we'll, as I say, we're going to be looking at bonding structure and properties, which is, there's quite a lot here, and it covers really a couple of topics. Topic 4, bits of topic 5 as well. Okay, so let's. I'm going to go through the basics first of all, because I'm not going to spend too long on this. There is actually a much more detailed video on ionic and covalent bonding that you can watch. That's actually on the GCSE sessions, and I think it was GCSE spring 2021. So if you're not sure on your bonding, which hopefully you are, you can go watch that as well. Okay, so they bonds get this noble gas configuration, chief or valency. What I've done here, I've just done a link to what you did at GCSE, and then you can just see there's actually a massive kind of crossover into what we do at A level. And sometimes it feels like I'm teaching a GCSE class because the content's so close. But obviously we extend it at A level. We go into a bit more detail. So let's move on to the next slide. So we're going to start off with this model of bonding, and hopefully your head is already saying, all right, we're looking at ionic bonding. So these are kind of models that we'd expect to see ionic bonding. And as I say, this is I've just literally lifted these slides off the GCSE slide, so I'm not going to take time on them. If you want to watch the video, you can, or the presentation. So it's always between a metal and non-metal. Annoys me that I see students at A level doing ionic when it should be covalent and vice versa. So please make sure you know the kind of bonding you are doing. It's got to be a metal and a non-metal. And I'll just point out, by the way, hydrogen is not a metal. We'll talk about that in a minute, maybe. There you go. So there's our bonding types. So this is from your A-level syllabus. Okay, so as you know, during the bonding process, we form ions due to the transfer of electrons, and those ions attract each other. And what they're trying to do is not only just trying to attract each other, they're trying to get as close as they can and maximize their attractions, but minimize their repulsions. All right, because you're going to have positive and positive ions. The positive ions are going to try and attract the negative, and they're going to try and avoid coming close to the positives. Okay, so here's our formation of the ionic solid. Like I say, please go back to your bonding diagrams, and that's on the PowerPoint as well at GCSE. You see you form these two ions here. When I draw my bonding diagrams, of course, and like you would do as well, we only draw the outer shell. We don't draw the inner shell. We don't need to. So we can see there we've got our stable structures. Similar for something like sodium oxide. That's the bonding diagram you want to draw for sodium oxide, and it is ionic. Sodium's a metal, oxygen's a non-metal. We're showing the transfer of electrons, and here we're indicating the charge. So a couple of things, make sure that you're accurate when you draw them. Yes, they're easy to do, but if you don't do them properly, you're not going to get the mark. Okay, so you can see here that wouldn't be a good bonding diagram because I need 2 sodiums. I've only drawn 1. Okay, so the A level. You need to recognise and draw the crystal structures for sodium chloride and cesium chloride. So if you have a quick look here, as we said, they form what's known as a giant ionic lattice. And so I'm just going to look at what these lattices look like. Just shut my door there, and we can see that this is a structure associated with sodium chloride. I'm going to talk about how to draw the lattice, and also I want to talk about this term coordination number. And if you read it, it's their coordination number is the number of ions that immediately surround an ion of opposite charge in a crystal lattice, or you could also say it's the number of atoms, ions, or molecules that are the nearest neighbours to a central atom. And because you're trying to maximise your attractions, the positive ions are going to be, the positive ions are going to be as close as they can to the negative ions, and the negative ions are going to try and be as far away as they can. Okay, so now I'm going to talk to you about drawing the structure. This is sodium chloride here, and if we look at the coordination number, You'll see the chloride ions are as close as possible to the sodium ions. So there's my sodium ion, the orange dot. The chloride ions are here. And you might not realise is that the sodium ions are actually further away than the chloride ions are, which is why they're not actually classed as, being nearest neighbours. So they're not part of the coordination number. So you can see they're actually quite far away, and that's to minimise your repulsion. Think of a triangle. That's the shortest side of the triangle, and we've got the hypotenuse, which is the longest side. Now, how to draw? Well, I'm going to skip that actually, because I'm going to show you how to draw it. You can go to a little link here that goes through it, but I've got a much easier way of doing it, which I've just discovered recently. So the way you draw your structures, you've got to be able to draw two. You've got to be able to draw sodium chloride and cesium chloride. And if I was asked to draw cesium chloride, I would draw something like this, okay, which isn't actually that bad. So let's bear me a second. I'll just show you. Well, that's not come out very well. So this is how I would draw my lattices for sodium chloride and for cesium chloride. And it's a much easier way of drawing them. In the past, I've told my students don't draw sodium chloride. It's so difficult to draw. And I'll show you why I've said that. If I just go back to my previous slide, a second, there we go. That's what I was trying to encourage them to draw, and this is what you'll see people trying to give you instructions on how to draw. If you're ever asked to draw cesium chloride, they say, well, draw this. Well, good luck, and it's going to take you a long time in the exam to do that. But looking at mark schemes, they accept these drawings. So this is a drawing for sodium chloride. It's much easier to do. Quite often they'll draw the box for you, but if you can't draw the box, it's not that hard to do, just to superimpose squares. And I'm just going to point out to you how to then put the ions on. So if you see this as the front of the cube, you'll see they put a chloride ion here on one corner, and they put the other chloride ion in its opposite corner. And the same with the sodium ions. So we've got a sodium ion in this corner, and then a sodium ion in the opposite corner. And then in the square behind, it's the opposite. Okay, so we've got a chloride behind the sodium, and we've got a sodium behind the chloride. And that's a really, really easy way of drawing the structure. And if we come to the cesium chloride one, very easy to draw. Again, just draw your box, and in the middle, put your either your cesium ion. In this case, I've got the cesium ions and the chloride ions on the outside. You could do it the other way around, so you can mark that as being your chloride ion with the cesium ions all the way around. Okay, and these structures give us coordination numbers that you do need to know. All right, so you need to be able to quote those coordination numbers. And if I just go back, the coordination number of the cesium, you can easily see it's 8, 8. So for every 8 cesium ion, there's 8 chloride ions. And for the sodium chloride coordination number, it's 6, 6. So you must be able to quote those coordination numbers, and it is actually worth being able to draw those diagrams. So they're not too bad. Okay, just a few brief points about properties. Again, goes back to YouTube. Not YouTube, sorry, I was reading something else there. It goes back to year 11, but they have high melting points due to these strong attractions, and they only conduct when molten or dissolved. And I've just put here as well something that's definitely worth knowing from your GCSE as well for your A level. It's looking at the melting point of a group 1 and group 7 salt compared to a group 2 and group 6 salt. And as you can see there, you've got a much higher melting point with group 2 and group 6, and that's because of the ions. There's a greater difference in charge, and that results in stronger attractions or electrostatic attractions between the opposite ions. So you're going to need more energy to melt that substance. And then once it is molten or dissolved, which you can use water to break up the lattice or heat, once those ions are able to move, then they are able to conduct electricity. Okay, so going back to GCSE. Here's an A-level question though. State and explain which of the two following elements combine to form the most ionic bond. So hopefully you know that potassium, not potassium, sulfur and chlorine would actually be covalent in nature. So we've got the choice here. It's something that's going to bond together, a metal and non-metal, to be ionic. And what we're looking for here is the biggest difference in electronegativity. So we'll look at a periodic table of electronegativity in a moment, but as you should know, electronegativity increases across the periods and also up the groups. So we've got potassium on the far left and the chlorine on the far right. So they've got the biggest difference of those two. Okay, and then we've got a question here about the structures, the lattices for cesium chloride, and why is it different to sodium chloride. And the reason is it's the different size of ions. So, you know, if you think about packing two similar sized balls, perhaps tennis balls in a box, and then how they'd arrange compared to how you'd stack perhaps tennis balls and maybe a basketball or a football in the box, it would have to arrange differently. So it's due to the different size, relative size of the ions. Sodium ions and chloride ions are quite similar in size. Cesium ions and chloride ions, the cesium ions are much bigger, so it has to arrange them much more differently. We'll come on to the diamond and graphite a bit later. Okay, so that's your ionic done. Brings us on to our covalent, and we'll just make sure that we know covalent is when you have non-metal atoms joined together. And one of the mistakes I quite often see with pupils is they'll try and do ionic bonding with hydrogen, and hydrogen is not a and I think that's because when they draw the hydrogen, it's got one electron in its outer shell, so they kind of link it to lithium, sodium, potassium, which are also group 1 metals, and their head automatically goes into ionic. Just remember, hydrogen does not do ionic bonding. It won't give up that electron easily. All right, so it's going to use it to share. Okay, so let's go through those quickly. You can look at those yourself. So these are the sort of diagrams we'd expect you to be able to draw, particularly this one here. To show your covalent bonding. Again, if you're not good at covalent bonding, practice drawing them, or go back and look at previous carbon culinary session I mentioned earlier. So you've got methane here, CH4, you've got H2O, water, and you've got oxygen. Okay, so this is covalent bonding, and what we've got here, as we get with most covalent bonding, is we form what we call simple molecules. Right now, the forces within that molecule, what we call the intramolecular force, the covalent bond, is strong. A lot of people mistake it as being weak. It's not. It's incredibly strong. Okay. In fact, it's quite often stronger than an ionic bond. So the force within the molecule holding those atoms together is strong. And what is that force? Well, the force, you have got a hydrogen molecule here, and you can see you've got the two nuclei. This electron belongs to this atom. This electron belongs to this atom. All right, and what's happening is in covalent bonding, you're sharing electrons, so you're merging your valence shells, and then you get the pull of the nuclei to both the shared electrons, and it's that force of attraction that holds the molecule together. You do have repulsive forces in this molecule as well, so you're going to have repulsion between the two nuclei, you're going to have perhaps repulsion between your shared electrons, but the attractive forces outweigh the repulsive forces. So I would say at GCSE, you wouldn't have to describe a covalent bond, but at A level, perhaps you would be expected to be able to describe a covalent bond. So it's it's a bond that forms from the shared electrons in the valence shells of two atoms, with the attractive force of the nuclei to their shared electrons holding the molecule together. As I say, make sure you can draw these. These are typical. They're not the only ones that you're going to be asked to draw. This is a really good one to know. It's quite difficult to draw. And obviously, again, I wouldn't bother drawing the inner shells with these. So I thought I'd made a mistake then with this here, but I wouldn't put those inner shells on typically. So just do the outer shells, not the inner shells. So let's go towards a bit more of the A-level side of covalent bonding then. So we've got here boron trifluoride, and you might think, there's an issue here. There is an issue. Boron has only got 3 electrons to bond with, and so that's all it will form. It can only form 3 covalent bonds. So if it's the bond to fluorine, we get this substance or this simple molecule BF3. And if you look at the BF3, you'll think, well, hang on, it hasn't got 8 electrons, and that does happen in chemistry. We describe that as being valent or electron deficient. I tend to use the term electron deficient. So it's electron deficient. It's missing electrons from that shell in order to get full outer shell. So this allows it to form what's called a dative or coordinate bond. On your syllabus, it's called a coordinate bond. And you can see here, it's a bad animation this, but you can see I've got my 2 lone pairs here. There's room for them to actually interact with this nucleus. They can come onto this valence shell, and then we've got this interaction of these electrons with this nucleus, which is good, it's favourable, releases energy. So their orbitals overlap. Okay, so let's look at what that might look like. Again, I've got another molecule here. I've got ammonia, and you can, well, sorry, it's the same molecule. It's got our BF3, and you've got your ammonia coming in with its lone pair, and you can see how that lone pair has actually formed a covalent bond. So as I say, this is it's actually called a coordinate bond or a dative bond. There's the lone pair there. Those are the 2 separate species. And let's go back. You need to be able to describe a coordinate bond. It comes up quite often. So it's a covalent bond in which both bond pair electrons come from one atom. So in this case, they're coming from the nitrogen. Okay, so it's a covalent bond in which both bond pair electrons come from one atom. And that means now our boron is no longer electron deficient. Okay, here's carbon monoxide. And you can see here, it's not quite finished yet. I've done a bonding diagram here, and if you look at the carbon, the oxygen, sorry, you'll see that its valency has been achieved. It's got that full outer shell, 8 electrons. But if you look at the carbon, you can see it's only got 6 electrons. So what happens is the oxygen is very kind, and it actually says, well, look, I've got these spare electrons, these lone pairs. I will bond to you with them because I can interact with your nucleus and there's room on your shell for me to do that. So again, we have this dative bond forming. So carbon monoxide is a good example. And on the exam, if you look at the syllabus, they want you to be able to, draw some examples to demonstrate coordinate bonding. So carbon monoxide is a good one. I wouldn't go for the previous one with the ammonia and BF3. That's quite difficult to draw. This is another good one to use. So it's molecules that have H+ ions, which you'll hopefully recognise from acids. And you can see here, if you've got a hydrogen atom, if you've got H+, it doesn't have any electrons, but it does have a nucleus that electrons would like to interact with. So again, H+ is what we call electron deficient, and therefore it will form dative bonds. So another good example of a molecule that forms coordinate or dative bonds is this. So we've got ammonia with its lone pair, and you can see now that the hydrogen or the hydrogen nucleus, the H+ ion, has bonded. Okay, and again you can see here's another one. So this is a H+ ion, and again you can see that dative bonds formed. Now I need to look at those diagrams just again very quickly, just so you know. This, once it's bonded, once it's done the dative bond, you form what's called the oxonium ion, and it's actually got a formula H3O with a positive charge, which I really should have shown on there with the square brackets. So it's H3O plus now. It's gained that H+ ion. That's another good example of a dative bond. And it was the same with the ammonium as well. So we go back to ammonium. When that, wait a second. When the H+ ion comes in, that's NH4 plus. Okay, it's gained that H+ ion. Again, another good example of dative bond. So yeah, pick one of them and make sure you can draw it. Okay, so we're going to come on now. Again, a little bit of GCSE. We're going to look at the properties of these simple molecules in terms of melting and boiling points. And as you can see, these simple molecules tend to have these low melting and boiling points, but they do have a boiling point. There is a point at which they will become a liquid. Okay, if you cool them down enough, but you've got to go to quite low temperatures. So what's holding them together as a liquid at these really low temperatures? Well, there must be a force, a very weak force, but there's a force. Otherwise, they wouldn't liquefy. Why would they? So they do attract each other. And I've got carbon dioxide here, and you can see that we've got these molecules. I've got 1, 2, 3, 4, 5, 6 molecules with these really strong covalent bonds holding those molecules together. But there are only these weak forces between the molecules, and it's these forces, these weak intermolecular forces, that break during melting and also break during boiling. And it's also these molecules that if you cool something, these forces that if we cool something down sufficiently, become strong enough for the molecules to be held together as a liquid or a solid. So it's the intermolecular forces that we break or make in a change of state. So what we're going to do then is we're going to look now, that's a kind of a GCSE picture. We're actually going to explore those different forces that hold these molecules together. And there's 3 types of intermolecular force, but they all arise due to uneven distributions of electrons in atoms or molecules. So we're going to explore now what causes these uneven distributions. So the first one is this molecule. This has an uneven distribution of charge. And we say that it's a polar molecule, and the bond between this hydrogen and chlorine, which hopefully you know is covalent, would be described as a polar bond. So why has it got an uneven distribution of charge, and what's going on to cause that? Well, it's the difference in their electronegativities. There's a sufficient difference that the electrons are being pulled towards one of these atoms more than the other, and hopefully you know which electron which atom the electrons are being pulled towards. But we'll just have a look at our patterns, which I did mention to you we were going to look at. There's our electronegativity increasing up the groups and across the periods, with fluorine being the most electronegative element there. And we've got our chlorine here, so you can see it's on the far right. So this is the electronegative. So in our covalent bond, where the electrons are being shared, the electrons are being pulled more towards the chlorine than you'd expect. And that's because it's electronegative nature. So as I say, we describe it as being polar covalent. Sometimes people call it covalent with ionic character, because there shouldn't be charge in a covalent bond, but there is, because it's uneven pull. So we can mark these with what we call a dipole moment. You can see the hydrogen's got the positive dipole and the chlorine has got its negative dipole. And it's these dipoles that that will hold your molecules together. These weak attractions between the negative and positive dipoles. And I would call these dipoles, they're called permanent dipoles, because the chlorine is always pulling that electron towards itself more than the hydrogen can. Don't forget, this is a covalent bond, by the way. Lots of people don't realise that this is our dot and our cross. Dot from the hydrogen, cross from the chlorine. And the chlorine is pulling that cross and that dot towards itself. So you have these, what we call permanent dipole attraction. I'm just going to talk to you then very quickly about a little issue that there is, and it's to do with molecules having polar covalent bonds in. So we've got two molecules here. We've got carbon dioxide and we've got water, and they both have polar covalent bonds in. But the carbon dioxide is not classed as a polar molecule. It does have polar covalent bonds in, but because of the symmetry of the molecule, those and the vectors of the way the charges are being pulled, they cancel each other out. So there's not actually any side of the carbon dioxide molecule that's actually classed as being more negative than the other side. So we would describe carbon dioxide as being a covalent molecule that has polar covalent bonds, but the molecule itself isn't polar. Whereas if we look at water, water's different. Okay, so water also has polar covalent bonds. In fact, has very polar covalent bonds, as we'll see in a moment. But because of the vectors in the way the electrons are being pulled, you can see here that the negative charge is, the molecule's not perfectly symmetrical, and we've got negative charge being pulled up to this side of the molecule here, and that's making this side of the molecule relatively positive. So that will make that molecule polar. So I've just done a little picture here of some molecules that we would describe as being polar or non-polar, and you can see where the molecule is not symmetrical for all points. We have it, and you've got a polar covalent bond, would be classed as polar. This is this molecule here is symmetrical for all points, so we're going to describe it as non-polar. This molecule here is non-polar, okay, because we've got these vectors in pointing in particular directions. Whereas here, if you look at the this molecule, and hopefully, well, I'll be doing a lesson on this in the near future on VSEPR, but this is pyramidal, this shape. And if you don't know why it's pyramidal, then come to the next session I do. But again, this isn't perfectly symmetrical. So you have one side of the molecule that's positive compared to the other side of the molecule, which is negative, and you can see that here as well. Okay, so these are, you know, they all have polar covalent bonds in, but not all the molecules are classed as polar. It's kind of weird, but there you go. There's a nice little video there if you want to copy that link on the PowerPoint and go watch that to have a bit more discussion about polar molecules. All right, let's look at these molecules then. Do they exist as liquids? Can we solidify them? Well, yeah, absolutely we can. You know, if we cool nitrogen down, we get liquid nitrogen, liquid hydrogen. Bromine is a liquid at room temperature and iodine's a solid. So what's causing their uneven distribution? Is it a difference in electronegativity? Obviously not. They're the same element joined together. So there's going to be an equal sharing of the electrons. So how do they form forces of attraction? What's their unequal distribution of electrons resulting from? Okay. This bonding here is described as pure covalent bonding. As I've said, the electrons are being shared equally. So there's no ionic character, there's no polar character. This is pure covalent bonding. And obviously, therefore, these are non-polar molecules. So how do they get held together? And as I've said, you know, do they stick together? Yes, even at room temperature, they can stick. There's enough force to hold them together as a liquid at 25 degrees C, and even as a solid at 25 degrees C. So some of these forces must be actually pretty strong. So let's explore where they come from. Well, these are what we call induced dipoles or temporary dipoles. Sometimes they're called London dispersion forces. There's lots of terms that people use to describe this, and it's due to, and I always have this really important keyword when I talk about induced dipoles, fluctuation. We have fluctuation of electrons, and you can see in that molecule there on the right hand side. I'll just show you again. If you look on the right hand side, electrons are constantly moving, all right, even in the atom or a molecule, and at any one point we might have more electrons on one side of our atom or molecule than at another point. And what that results in, you can see another one's moved across. Okay, there we go. That side of our atom or molecule has now got a temporary negative dipole, and the other side of the molecule, of course, has a positive dipole. Now, what's going to happen, and this is where the term induced comes from, is that this atom next to it at this point doesn't have any charge, all right, because we've got a pretty even distribution of electrons. But because this side of the molecule has become negative, you can see electrons are being repelled away from that negative charge. And the result of that is now that that side of the molecule has become delta minus and that side delta plus. And now we have our attraction. And that's what holds things like iodine together as a solid. It's called an induced or temporary dipole or London dispersion force. And you can see this is now being induced in here. Now what you've got to remember though is that electrons are constantly moving, and so these will break. So they form and reform and break and reform, break and reform. This is why we call them temporary dipoles. And I've just put there an explanation of, you know, how temporary dipoles form. So boiling points. Boiling points. If you look here, I've got the noble gases. We're going from the top of the group to the bottom of the group, and you can see as we got a negative scale here, by the way, in temperature, you can see our boiling points are increasing as we go down the group. And you need to know why that is. And this is a consequence of you having more electrons as your atomic mass increases. So you think about helium, it's got 2 electrons, come down to radon, well, it's got a fair few more. And what that means is that you have bigger fluctuations. And the bigger the fluctuations in your electrons, the bigger the dipole and the stronger the attraction. Okay. And we can see that in group 7 as well. It's quite often something that people look for. We can see again our melting points, boiling points increase due to the greater molecular mass, indicating that there's more electrons and bigger fluctuations. I know it's quite commonly asked for, that kind of idea. And what I've done here, it's a link into your topic 5. Hopefully you'll recognise that as being iodine. So you have your iodine molecules being held together with their strong covalent bonds, and we've got these induced dipoles that, because iodine's got such a big MR, so many electrons, are actually held into a lattice. Okay, so that's iodine crystals. How big a difference? Well, it depends which textbook you read. Typically, this is what I found, and you don't need to know the big difference, what the difference has to be. But that's a kind of a good gauge for it. What I tend to say is it's worth knowing, carbon joined onto a halogen, we'd class as polar. Carbon joined onto hydrogen, we wouldn't class as polar. That they would be classed as non-polar covalent bonds. All right, so but take that with a pinch of salt. Just kind of have an awareness. Joined up to carbon and hydrogen is a non-polar bond. So what we're going to do then, just very quickly, we've got 15 minutes left, so it's going quite well. What I've got here then, we're going to look at the hydrides now of groups 4, 5, 6 and 7. And actually there's one thing before I talk to you about what I'm about to go on to, I just wanted to say something. I wanted to go previous, next. I wanted to say something to you about induced dipoles and permanent dipoles. You can lump them together under the term van der Waals forces. And, looking at mark schemes, you don't, if you're asked, what are the intermolecular forces in iodine, you can just say van der Waals forces, and the mark scheme accepts that. But you can also, go into further detail and say, well, it's actually an induced dipole. Either will be accepted. So I'm just pointing that out to you. And the other thing I want to point out to you is molecules. All molecules, from water to hexane to hydrogen, they all form induced dipoles. All of them have them, but things like hydrogen chloride or water or anything where you've got a different electronegativity not only has those induced dipoles, they have icing on the cake. They have their permanent dipoles taking place as well. So don't think, oh, that's got permanent dipoles, that's all it's got. No, it's going to have induced dipoles. It's got electrons. It's going to have induced dipoles. So I just thought I'd just go back to that for you. So if we look here then, we've got the hydrides of groups 4, 5, 6 and 7. And what I mean by hydride is basically they're joined up to hydrogen. So you've got hydrogen sulfide and so on, hydrogen chloride, and yeah. And if we look there, as we go down a group, so let's say we look at the green group here, you can see that our boiling points are increasing down the group. And we can see that as well with group 6, and we can see it in group 7 and group 5 and group 4. So as we go down the group, our boiling points are increasing, and you'd expect that. And I hope you can know or already knew why. The bigger the MR, the more electrons, the bigger the fluctuations, the stronger the induced dipoles, or the stronger the van der Waals forces. So what we're going to do then, what I'm missing off here, and you may have seen it when I flipped the slide too far ahead, where would you expect the hydrides of carbon and nitrogen and oxygen and fluorine to be? Well, being at the top of the group, not having many electrons, I'd expect them to be even lower. So I'd expect them to be somewhere down here. Okay, let's have a look. All right. Carbon is exactly where I expected it to be. It's got a smaller molecule, less electrons. Yeah, when we look at the nitrogen and the oxygen and fluorine, we actually see they're actually a lot higher than we would expect. Okay, so why is that? Well, we've got a permanent dipole on steroids, basically. It's what's called a hydrogen bond. Those molecules that you can see on the graph there can hydrogen bond, and this is a very, very strong intermolecular force. So let's look at what a hydrogen bond is. Well, I would highly recommend that you learn how to describe a hydrogen bond, because examiners ask it all the time. You know, I've got my own one that I know to say to examiners, and I suggest you get a good one for yourself. The best place to find a definition is off a mark scheme. You know, go on to your question bank search, type in hydrogen bond in. I'll guarantee you there'll be a question that says, what is a hydrogen bond? And learn that, okay, and make it yours. So I'm going to talk to you about how to draw hydrogen bonds, because that's also something that examiners ask you to do. So you can see here I've got two water molecules, and it's not the best drawing, to be honest, of a hydrogen bond. Again, look at mark schemes. They're the best place to find diagrams. But you can see here we've got, when you're drawing your diagram, you've got to show your dipole on the water molecule. So you can see here I've got a delta plus and a delta minus on the electronegative oxygen. And you've also got to show your lone pair. And then we show the hydrogen bond with like a dashed line between the hydrogen and the lone pair. Here we've got HF. Okay, now that's not a good diagram of hydrogen bonding because it's missing some essential features. So hopefully, if you listen to the previous section there I just mentioned, you'll see that I need to mark on my dipoles. I'm going to show a hydrogen bond, show you dipoles. And then I've got my dashed line, and I might also want to put my lone pairs in there as well, because if the hydrogen is actually interacting without those lone pairs, okay, so it's not to the negative dipole, it's actually almost forming a bond to these lone pairs. It is not a covalent bond though. Please don't think it's a covalent bond. It is about a tenth of the energy of a covalent bond. Here you can see some ammonia molecules that also form their hydrogen bonds to each other. So there we go, that's our hydrogen bonding, and that explains, it's like I say, it's a very strong intermolecular force. That explains where they're not where we'd expect them to be if we only had induced dipoles and permanent dipoles holding our molecules together. So that's our graph. Now I'll just point out to you, why doesn't carbon have this? Well, if you go back to your definition, your hydrogens must be attached to very electronegative elements, which include nitrogen, fluorine, and oxygen. Carbon doesn't have that electronegativity to cause the positive dipole on the hydrogen. So that's why it's where we'd expect it. So again, coming to topic 5, I'm just laughing at my picture that I put in there. Going back to topic 5, we've got some water molecules here. And because these hydrogen bonds are so strong, and they have very particular orientations as well about how they form. Usually a hydrogen bond is at 180 degrees. And we end up actually forming this kind of tetrahedral structure. You know, you recognise this perhaps as diamond. Diamond's got a very similar structure as well. And it forms this lattice, this crystal lattice. And this is ice. And normally water molecules are tumbling around each other and they're not held in specific positions. But when we get to 0 degrees C, those intermolecular forces are strong enough to hold them in a lattice. And you actually find the water molecules are actually further apart in that lattice than they are in the liquid because of how they're held. And this is why water freezes when it expands. Water actually has a lower density as a solid than it does as a liquid. And you can see here that the water's expanded and pushed the top off our milk bottles, okay? And then I'm just going to show you here 2 molecules, similar MRs, so we expect similar induced dipoles. But hopefully you'll recognise that this molecule here will have a high boiling point. Can you see why? Well, hopefully you'll see that it can hydrogen bond. Okay, and you can see the extent that the hydrogen bonding has on the on this alcohol ethanol. And what I've done here is I've just drawn another diagram because, you know, examiners want you to be able to draw these sort of things. So I've drawn a diagram for showing hydrogen bond between 2 ethanol molecules, and you can see, you know, I've put the key things on. I've got my lone pairs, I've got my dipoles, and my dashed line for the hydrogen bond. There you go. There's a question. I forgot to put that into this PowerPoint, and that's a mark scheme answer. Learn it. And there's a question for you as well from the question bank search, and I won't go through it with you. I've actually put the answers there for you. I thought I did. If not, I'll try and add it into the PowerPoint slide that you can download. Okay, let's skip that. We don't need that. All right, so that's your intermolecular forces. So I was going to finish off now, just very quickly. Again, it's GCSE. We're going to talk about carbon allotropes. This is from your topic 5. So you'll recognise these as diamond and graphite. Or hopefully you recognise them as diamond and graphite. And, you need to be able to describe the bonding in these substances. So I'll put some key features on here about, what graphite looks like. We'll explore that in a minute. Properties from GCSE and uses. That's on the PowerPoint. I'm not going to go there too much. Okay. Properties of diamond. Okay, well, one of the things I've just told you there, I'll flip through there, it's a very hard substance. And you need to know how the carbon atoms are bonded in diamond. It's a giant covalent. I describe it as a rigid 3-dimensional lattice with strong covalent bonds in all directions. And that explains why diamond is so hard. It's graphite soft. And again, hopefully, you know how to describe the bonding graphite. Carbons are bonded to only 3 other carbons with their 4th electron delocalized between the layers. Learn that, you can be asked it. And what you're seeing here in graphite is these delocalized electrons between the layers and these weak forces. And it's those weak forces that make graphite soft because they allow the layers to slide over each other. So graphite is described as soft and slippery. Okay. And those delocalized electrons also allow graphite to conduct electricity and also conduct heat. Okay. Metallic structures. I've seen some awful pictures of metallic bonding. If I'm asked to draw a metallic structure, something like aluminium or sodium or magnesium, well, this is the basic idea that I would have. So you've got the positive metal ions in a sea of their delocalized electrons. And don't confuse it with ionic because, obviously positive, negative charge. But with our negative charge holding our positive ions together is the delocalized electrons. That's our metallic. In ionic, what's holding our lattice together is the attraction between positive and negative ions. Okay. So, yeah, make sure you don't get them mixed up. So properties of metals. Again, it's GCSE, but hey, it's going to be on your exam. It was on my mock for my pupils this last week. So let you read through that. They're basically delocalized electrons allow them to conduct heat, electricity, and it's what gives them high melting points is the attraction, the electrostatic attraction between the positive metal ions and the delocalized electrons. And I'm just going to point out to you, and I've got it there. One of the things that you might be asked is, why does some like magnesium have a higher melting point than sodium? And hopefully you'll see that it's because of the positive charges on the magnesium compared to the sodium. A bit like your group 1, group 2, group 6 ionic compound. So you've got this stronger attraction between the greater positive charge on the cation. So you're going to need more energy to break it. And then the other thing I was going to say as well is as you go down a metallic group like group 1 or group 2, your melting points actually decrease. And the reason for that is your positive charge, your ion, is much bigger. And as a result, if you go down to cesium, which melts in your hand, that positive charge is spread over a big area. So you don't have that stronger electrostatic attraction. And then the final thing we'll talk about, I think it's the final thing, is another property of metals. And I'm just going to not even say the word. Hopefully you can tell me what that property is. That's malleability or even ductility. And the way I describe or explain malleability or ductility is that the electrons are a constant presence and allow the ions, and because the ions are in a lattice, the ions can slide into new positions. So what I say is the lattice allows ions to slide into new positions with the delocalized electrons as a constant force holding them into new positions. Again, it's a good thing to learn. And that's it. I think, yeah, I've got a little GCSE question there. If you want to have a go at doing that, you're more than welcome to, using melting points, boiling points, properties, names. You should be able to name things.